Bismillah ar-Rahman ar-Rahim. This is the second video of chapter number 8. We stopped at this slide last time, and this will show you two arrangements, two water treatment processes. The first process is to treat surface water, and what I mean by surface water, I mean rivers water, lake water, okay, anything above than the surface. Or the second process is treatment of water with high levels of dissolved constituents. Okay, what I mean by this is, for example, treating brackish water, okay, the water underground that has a lot of dissolved constituents. Let's look at the first treatment of a regular river. In the US, the water that comes from rivers and lakes, they have to treat it before they send it to the public. So, for surface water, the influent comes from the surface water in pipelines to a screen. In the screen, they screen large objects, they screen particulate material out of the water. And then all this will come as waste, the particulate matter. The water will come without particulate matter. Here they will do pH control, and they will do oxidation and disinfection. And of course, after that, it goes to a rapid mix. A tank where you add coagulant, and we'll be talking about coagulation later on. And then they do a rapid mix. Later on, there is the flocculation sedimentation tank. Once they add the coagulant, all these material that's suspended will be flocculated into a flock, and then they will settle down in the flocculation sedimentation tank, and you can see that solids will be wasted. After sedimentation flocculation, you'll add polymer. The main reason for this, and you want to make sure that anything that's dissolved inside the water will be coagulated again, or the polymer will make some chemicals around it, and they will stick with other particles, and then the granule filtration will trap it. Of course, once you do filter clean or filter backwash, you will have filter wastewater. So the clean water after the filter, it will come to another oxidation disinfection, and then clear water storage, and then sent to the public. This filter backwash, they take it from the storage tank to backwash the filter. And also, the filtrate waste, it goes recycled back to the rapid mix too. So it's different processes between surface water and brackish water. Let's look at the next one, brackish water. First, you can see here, they do pH control, oxidation disinfection, and then they will start with a cartridge filter. Later on, they will have membrane models like nanofiltration, ultrafiltration. And of course, anything that will be trapped by the membrane, it will be disposed as solids. And then later on, you'll have RO, reverse osmosis. Still, it's another membrane, but the pores are very tiny, very small. Of course, anything that will be trapped by the membrane will be concentrated as a brine wasted or discharged. Later on, you'll have oxidation disinfection, and then stored in a clear well storage, and then to the public. So these are possible two processes. Of course, this could be rearranged, or one process would be added, and some of the process would be cancelled. Well, that's up to the engineer of that plant. Let's look at the first process, coagulation flocculation. What is the meaning of coagulation flocculation? Well, in coagulation, we are removing particles, and we are removing a portion of dissolved organic matter. Coagulation and flocculation, you are removing particles and a portion, some of the dissolved organic matter. Of course, coagulation and flocculation should be followed by sedimentation and or filtration. Now, let's take each one of them as a simple definition. What is coagulation and what is flocculation? Coagulation, remember that most of the particles inside the solution has a negative charge. So coagulation is charge neutralization. We are trying to neutralize this negative charge. That involved, we are doing also, because we are doing charge neutralization, we are doing conditioning of the suspended and colloidal and dissolved matter. We are preparing these solids for something else later on, which will come, the flocculation. So coagulation is a charge neutralization step. Flocculation, now, once you neutralize all these particles, now we need to do aggregation of destabilized particles. And of course, formation of large particles, we call this floc. So these particles, okay, they will aggregate and then they will make larger particles. We call this floc. So the surface charge of this coagulation flocculation process is the main contribution of this method. Of course, the end of it is to make the particle stable. Of course, these stable particles are likely to remain suspended in solution. And of course, this measurement is either turbidity or total suspended solids. And these suspended solids and fine particles are always stable and cannot flocculate, okay, and cannot settle in a given time. And how could you change the stability of these particles? Of course, everything depends first on the balance of the repulsive and attractive forces between these particles. If they all have negative charge, you can see that they all will repulse from each other. So, and these particles, as we just mentioned, that they have a negatively charged particles. So therefore, repulsive electrostatic forces exist between these particles because they have the same charge. After you add the coagulant, this repulsive force will become minimum. And then particles will come together and rapid flocculation can occur. Okay? So this coagulant is added to destabilize particles and accomplish coagulation. Of course, there is a lot of coagulants. Selections of the proper one depend on what? What is the characteristics of this coagulant? Some coagulant is good for certain organics and inorganic in water. Of course, not only that, concentration and type of particulate. How much particulate we have in water. The concentration and the type. Concentration and characteristics of natural organic matter. Water temperature is also another factor. Water quality, for example, pH. Cost, of course, and availability. And at the end, when some coagulant will give you huge amount of solids precipitated. So we need to check the dewatering characteristics of these solids that are producing. Some of them will be producing already dewatered sludge. Sludge means solids are precipitated at the bottom of the tank. And some will have high water content of these solids. So we need to check which coagulant we want to use for what type of organic or inorganic in water. Type of coagulant is an inorganic metallic coagulant, for example, aluminum sulfate. They call this alum. Okay, this is the chemical structure of alum. Sodium aluminate is another one. Aluminium chloride is one, ferric sulfate, and ferric chloride. Prehydrolyzed metal salts. This is made from alum and iron salt. They added together. And of course, hydroxide under controlled conditions. This include polyaluminum chloride, polyaluminum sulfate, and polyiron chloride. Organic polymers is another type of coagulant. Cationic polymers, anionic polymers, and non-ionic polymers. This is for synthetic polymers, molecular weight 10 to the 4, 10 to the 7 gram per mole. These organic polymers, I use them. They are really good in removing dissolved organic. And the fourth one is to use a natural plant-based material. Okay? And these are used in most of the developing worlds. Sometimes you add the coagulant, but you need some help. You need some aid, flocculant aids. So these aids help enhance the coagulation and flocculation processes. Coagulant aids are example of clay, of course, insoluble particulate matter, diatomite, powder activated carbon, fine sand. This will help form nucleating sites to form large flocks. Of course, these flocculant aids, such as anionic, non-ionic polymers, are used to make the flock very strong. We don't want to make a flock that's very weak, that will break in the middle of the tank. And of course, these are added after you add the coagulants and the destabilization of the particles. And the most chemically used coagulant is aluminium sulfate, alum, with a molecular weight of 594 gram per mole. So, there's something called a jar testing. Hopefully, we'll do it in the lab. And this jar test is widely used to screen what type of coagulant you're going to use and what is the coagulant dosage, the best optimum coagulant dosage. This jar test contained of 6 batch reactor, 1, 2, 3, 4, 5, and 6. These are equipped with a pedal mixer that can turn at variable speed. You can see that the variable mixer here. So there is a mixer that is used to mix the water at variable speed. Okay, so now we're going to be adding different dosages of coagulant at the water sample. Remember, what's the objective is to remove turbidity, for example, or to remove suspended solids. So let's add the coagulant at different variable concentration. Let's see, 0% coagulant, 5% coagulant, 10% coagulant, all the way, let's say, to 25% coagulant. Once you add these different variables of concentration of coagulant, now the rapid mix is combined with the additions of the coagulant to mix the coagulant with the water. At the end of this, you'll have a slow mixing stage to enhance flock formation. And then at the end of this, everything will be stopped. So the flocks will be settled to the bottom of the tank. You can see that settling at the bottom of the tank. This settling is under quiescent condition, quiet conditions. Nothing is interacting with these flocks. Nothing is hitting these flocks. Nothing is breaking these flocks. And then the settled supernatant is measured and plotted as a function of the coagulant dose in order to determine the proper coagulant dosage. I think it's good to show an example so you can see exactly what's happening here. Let's look at this jar testing to determine the optimal coagulant dosage. Jar test was conducted on an untreated water Initial turbidity is 10 NTU, that's huge. Alkalinity SCO3 concentration is 50 milligram as CaCO3. Using the following data obtained from the jar test, estimate the optimum alum dosage for turbidity removal and the theoretical amount of alkalinity that will be consumed at the optimum dosage. Alum is added as a dry alum. Molecular weight is 594 gram per mole. The alum dosage in milligram per liter: 5, 10, 15, 20, 25, 30. And you can see the turbidity goes from 8 down to 6, down to 4.5, down to 3.5, which is nice. At the end, you can see when you increase the alum dosage from 20 to 25, the turbidity will increase from 3.5. Which means that if you add too much coagulant, it will have a reverse effect. The flux will be broken back and they will be suspended. So you will increase turbidity every time you don't add too much coagulant. There is an optimum coagulant. Beyond that point, coagulant dosage cannot help anymore. And you see if you add to 30, it will increase from 5 to 7. So let's look at the graph to show. This is turbidity NTU in the y-axis, and this is the alum dosage in the x-axis. You can see that the turbidity is decreasing with the alum until it reaches a minimum. So we are looking for this minimum. So the turbidity minimum is 3.5. You go all the way, and this is here. So you could find the alum dosage, 20 milligram per liter. So you could see the operator for this type of untreated water use 20 milligram per liter of alum dose. Now remember, here he told you that there is alkalinity, and this alkalinity has a value of 50 milligram per liter as CaCO3. So we need to know, because alum is famous, alum will react with alkalinity and will reduce it, and we need this alkalinity in water. So if alum gonna treat turbidity and also particles in water and dissolve materials in water, it also will react with alkalinity, and that's not good. So we need to know how much consumption of alkalinity out of 50, how much will be removed because of this alum addition. So in order to see the alkalinity consumed, we have to look at the equation first. If you have alum, Al2SO4 14H2O, it will react with alkalinity. That's the problem. Look at this. 1 mole of alum will react with 6 mole of alkalinity. This equation is balanced. Of course, to produce this precipitation and SO4, H2O, and CO2. So now we're going to use this equation to find out how much alkalinity consumed. The dosage is 20 milligram per liter alum. Of course, you convert milligram to gram, and then you divide it by the molecular weight of alum, gram per mole, and then you convert mole of alum to mole alkalinity. Remember, 1:6. This is by default. Alum, 1 mole of it needs 6 mole of alkalinity. Okay, and then 1 mole to 1 equivalent, and you multiply it by 50. Remember, if you want to switch it to as CO3, you multiply by 50 when you did the hardness. So this would give you 0.01 gram per liter as CaCO3, which is equivalent to 10 milligram per liter as CaCO3. So the 20 milligram alum will remove only 10 out of 50. So at the end, you will have sufficient amount of 40 milligram per liter as CaCO3 of SCO3 is enough to buffer the acidity, to fight the acidity that produced after the alum addition. There's other consideration that we have to take is the coagulant should be dispersed into the water stream via a rapid mixing system. We'll show it to you in the next slides. It's either bumped mixing, for example, bumped flash mixing. You'll see it here, the bumped flash mixing. The water is mixed by the chemicals and then bumped with the chemicals. So you could do a bumped, we call this a bumped flash mixing. So this is the rapid mixing, and here there is a diffuser plate. So the bumped water, there's the water's coming from here, that's right. And then you'll bump the water so it will mix with the chemical. And we call this bumped flash mixing. This is the bumped flash mixing that we showed in the previous slide, or a hydraulic method. For example, an inline static mixer. The inline static mixer, you can see that the water is mixed with the chemical. And you can see that here there is an inline veins that result in turbulence rapid mixing. And of course the mixed water with the chemicals are coming from the other side. Which is a simple, reliable, and non-mechanical. Third is mechanical mixing, which is conventional stir tank being the most common. Here in the conventional stir tank, you can see that the water to be mixed by the chemical coming from the bottom. And here you can see that these are the mixers. So these are rotating around, and the chemicals are coming from these sides. And you can see that the chemicals are mixed with the water, and the water will come with the chemical at this side. So all of these are examples how we add the coagulants to the water stream via the rapid mix systems. The gentle mixing on the other side is a very good key for proper flocculation. Of course, to assist particle aggregation, mechanical mixing is typically employed to maintain the particle in suspension. Okay? To allow all these particles to flocculate. This flocculation system can be divided into two groups, either mechanical flocculator, vertical shaft. We'll show you the vertical shaft. So this is the vertical shaft, you can see it. Vertical shaft. 1, 2, 3. So this is the influence from coagulation coming from here. And you can see that these are the vertical shafts. At the end, of course, sedimentation basin, and then a type of a vertical shaft is this foil type mixing blade. Or horizontal shaft pedals. The horizontal shaft pedals is this influence comes from coagulation, and here we have the flocculation. So this is the horizontal one, shaft pedals. Okay, they look like this. If you have a section, the pedal mixers look like this. So it's a horizontal, and the previous one was a vertical. Oops. The last one is hydraulic flocculators. You can see in the hydraulic flocculators there is no vertical shaft and there is no horizontal shaft. The water is coming from the coagulation process and moving. Here there is no energy. There is no mixing blades. The water, you're allowing the water to go as a black flow reactor, going from a place to a place. Look at this here. It goes from here to here. So it allows the water to be mixed very good with the chemical. Okay, and then leaves. It's like a maze. Leaf from here and leaf from here. Okay, let's look at design of a mechanical rapid mix tank. Conventional stir tank is used for a rapid mix in water treatment plant. The flow is 10 to the 6 liter per day, the water temperature is 10 Celsius, determine the tank volume, and he need to know the power. Of course, we always has to care about the power because the money is here. How much power is going to be consumed. Remember the hydraulic, this one, it doesn't need any power. Okay? So here you need to find out the volume. First of all, we should select how much time we need the water to stay inside the rapid mix. I'm going to assume 1 minute. Okay, it's a very good assumption. Tension time of 60 seconds is good for mechanical mixing. And I'm going to use mechanical mixing. So the volume is equal to the flow rate, 110 to the 6th liter per day, times the time, seconds. Seconds with second, you'll convert it to minute, minute to day. So day with day, of course, minute with minute, you'll end up with liter, and that is volume. Of course, you convert liter to meter cube. So the volume of this rapid mix is 69 meter cube. Now, we need to find out the power. The power equation is this G prime, the RMS velocity gradient, G prime square times mu times times the volume. Okay? This is the velocity gradient, RMS velocity gradient. Now, we have to look for a value. If you look at the table 812 for mechanical mixing, so I choose a mechanical mixing, or the table or the book actually find mechanical mixing. Of course, you have the options of inline mixings, horizontal shaft, vertical shaft. It's up to you, up to the designer. But for this book, he choose a mechanical mixing. So the RMS velocity gradient, the G dash, is from 600 to 1,000. So the book found 900, so which is a range between 600 to 1,000. So we choose 900 per second. And the detention time, we found 60 seconds. We are still in the range. So now we have to multiply G prime times T. So G prime times T, 900 per second times 60, second with second, you'll end up with 5.4 10 to the 4. 5.4 10 to the 4, which is between these values. So we are good. We are still within the guidelines, typical values for design of rapid mix. Of course, you have to check. If you are using inline mixing, you have to choose the RMS velocity between 3,000 and 5,000, for example, per second. And of course, it's for 1 second. That's the detention time for inline mixing. And the GT should be between 110 to the 3 to 110 to the 5. You have to check it. And the other ones is the RMS value for the horizontal shaft is from 20 to 50. Detention time 10 to 30 minutes. And then GT is from 110 to the 4 to 110 to the 5. And the other one is also included. So 900 square. Time the viscosity, because 10 Celsius will give you the viscosity of the water, times the volume. Of course, Newton of the viscosity can be changed to kilonewton, and then you will end up with 73 kilonewton per second times meter. This means 73 kilowatt. Okay? Now we come to the last few slides of hardness removal. The hardness removal starts as a two-stage excess lime with soda ash softening process. So there is a two-stage lime and a soda ash softening process. And the lime is sold commercially in the form of quicklime. The quicklime is 90% CaO. And also hydrated lime is 70% CaO. You can see that most of these things in the market is not pure. So it's not 100% CaO, it's only 90%. 10% is impurity. Sometimes you'll have a granule quicklime. this granule quicklime, you have to crush it and fed to a slurry containing about 5% calcium hydroxide. Depending on, do you have chemicals, water, or do you have a granule? All of this will be taken into consideration. And also the powdered hydrated lime is prepared by what? Fluidizing the tank containing the turbine mixers. So it's either granule, powdered. Now these are the types of the lime. Now let's look at the soda ash. Soda ash is approximately in the market 98% Na2CO3. That's nice. That's better than lime. It has a grayish white powder that can be added either with lime or following the addition of lime, either together or after that. At the end, once you add lime and soda ash together, or lime after and then soda ash, then you should add carbon dioxide. What is the reason for this carbon dioxide? Is for recarbonization. The objective is to reduce the pH and precipitate excess calcium of the lime softened water. When the slurry CaOH2 is added to the water, it first reacts with what? Look at this. It first reacts with CO2, because CO2 is a very strong acid than alkalinity HCO3 minus. This chemical reactions for the removal of carbonate and non-carbonate hardness is shown here. So we have lime react with CO2 to produce precipitation, CaCO3. This will precipitate. And of course, H2O. Now, lime also will remove carbonate hardness. You can see that here, the CaOH2 first reacted with CO2. Now here, it will also react with Ca. This is the second step. CaSCO3 too, to produce CaCO3 solids. This will precipitate, and H2O. And also, it will replace the magnesium with calcium in solution. Let's see. Also, the lime will react with MgHCO3 too to produce another CaCO3 precipitate and another MgOH2 precipitate. So we remove the magnesium here. And of course, H2O at the end. This is the carbonate hardness removal process. Now, the non-carbonate hardness removal process, if you have MgSO4, same thing, lime will react with it to produce MgOH2 precipitate, settled, and CaSO4. And now soda ash will come into effect. Na2CO3 to react with CaSO4 to produce CaCO3 precipitate and Na2SO4. This soda ash, you can see it, it was used to remove calcium, non-carbonated hardness. This might be presented in the untreated water, or may be the result of precipitation from the magnesium non-carbonate hardness. Okay, so we will stop at this point because this is going to be the next